Question 1. In how many ways can you arrange the letters in rolling? So far it seems relatively simple because there are 7 letters and that should just be 7 factorial. However, we have some restrictions. Part A, what if the R must be first and the G must be last? So we are going to make sure that we deal with that first. So part A, if the R is first and the G is last, we have 5 other letters that we want to arrange in there. And that's simply 5 factorial, which is, of course, 120. What if L must not be the 4th letter? So this one's a little bit challenging because it's telling you what can't happen. So really it's saying count all of the possible cases and take out all the cases where L is in fact the 4th letter. So what that is our total number of cases, so 7 factorial, subtract the number of cases where L is the 4th letter. So if L is the 4th letter, and I'm just going to write that here. So if L is the 4th letter, that means there are 1, 2, 3, that's L, 4, 5, 6 other letters that we are arranging around that. So really, that happens to be 6 factorial. So our answer here is 7 factorial minus 6 factorial, which is equal to 4,320. Question number 2, in how many 3-letter arrangements can you make using the letters from the word Hogwarts? What if you must not include the vowels? Okay, so Hogwarts without the vowels is HGWRTS. That's 1, 2, 3, 4, 5, 6 total letters, and I want to make a 3-letter arrangement. So arrangement implies that the order actually matters. So if we've got 6 total and I'm wanting to arrange 3 of them, that's 6 permute 3, which is equal to 120. What if you must include the letter H? So in every single arrangement, the 3-letter arrangement that we're talking about, the letter H has to exist. So here are 3 possible cases. H can be first, H can be second, or H can be third. And then around that, we can arrange, we are really just permuting 2 other letters into those spots, right? So in this case, it's 7 permute 2, and it's 7 because we're not going to include the H because the H has already been placed there. And then similarly, even though they're split, still 7 permute 2, and then 7 permute 2. And we're going to add all those cases up. And when you do, the answer is 126. But another way that you could approach this, so if there were more slots, for example, than just 3 and you didn't want to draw it out the way I did, what you can do is consider the 2 pieces of the actual puzzle. So piece number 1 is, how do I deal with my H's? And then piece number 2 are the other letters. So I'll just call that L. So in terms of H, we know since this is a 3-letter arrangement, there has to be, 3 different spots for H to exist. The first space, the second space, the third place. So if it was a 7-letter arrangement, you would just know that there's 7 spaces for the H to go. And then we're going to multiply that by the rest of the letters, or however they're going to be arranged. So I know that if I take away H, that's 7 letters, and I only have 2 spaces to permute them on now, so it's 7 permute 2, which also equals 126, because really, if you add that 3 times, that's the same thing as multiplying it by 3. So either is correct, or I guess both are correct. Question number 4, in how many ways could you arrange 10 different people, or how many ways could 10 different people be arranged in a criminal suspect line, so a police lineup, if there are no restrictions? So that's kind of just the first question, but not an actual question, because no restrictions is way too easy for us now. But that happens to be 10 factorial. Okay, but part A, if the shortest person must be first. So there is only one distinct shortest person. So whoever that person is has to be first. So they're kind of out of the arranging piece. We already know where they're standing. The rest of the 9 people is what we're looking at. And that in our case is 9 factorial. Because of course I'm arranging all 9 of the people. Which is 362,880. Shortest person must be first and tallest person must be last. So that's now 2 people taken out, so that's just 8 factorial. Something that's important to consider with these types of questions where it says first and last, if where first and last is not distinct, so if I have people lining up here, and this is first and this is last, great. Then it's exactly the way that we've considered it. However, if it really doesn't matter, so this could be last, this, side to the left here could be last, and then this side could actually be first, you have to multiply whatever your solution is by 2 because there are 2 cases, right? So it's whatever that is multiplied by 2 because you can flip the entire lineup the other way. Since in this case, people actually have to walk out to be seen in the criminal suspect line, there is an order that would be implied that's important to keep. So this doesn't actually apply for this situation, but definitely always something important to keep in mind. Part C, the 2 sketchiest people must be side by side. So again, with these 2 really sketchy people, they're the most sketchy of all of the people in the criminal suspect line. So if they're distinct, and if those 2 people are standing together, our approach is going to be that we're going to count them as one person. So if they count as one person, we're actually left with 9 people that we are organizing, and then because they can be sketchy 1, sketchy 2, or sketchy 2, sketchy 1, we have to organize the sketchy people. That's 2 factorial, which is 725,760. Okay, so part D, the 2 sketchiest people must not be side by side. So really, this is exactly what cannot happen. So our last question cannot happen. So all those cases can't be there. So what we're going to do is we're going to take the total number, whatever 10 factorial is, and we're going to subtract this 7,000. We're going to take away all the cases where they're together, and then we'll be left with the number of cases where they're actually apart, or the number of possible arrangements where these 2 sketchy people are not together. Which is 2,903,040. And part E, you can actually only see 6 of the 10 people that are there. So in this case, because we're picking sum of the total, it is a permutation question. So we have 10 total people and we're permuting 6 of them, which is 151,200. And finally, question number 5, how many distinguishable arrangements are there of each of the following words? A, Mickey. Since Mickey has no repeated letters and there are just 6 letters total, that is simply 6 factorial, which is equal to 720. Minnie, however, is a little bit different. So Minnie also has 6 letters. However, there are some repeat letters. So there are multiple N's. So there are 2 N's, so we're going to divide by 2 factorial, and there are 2 I's, so we're going to divide by another 2 factorial. And that's equal to 180. Okay, C, Goofy. So 1, 2, 3, 4, 5 total letters. And we're going to divide by the number of identical terms factorial. So in our case, we've only got 2 identical because they're the O's. So divided by 2 factorial. And that's equal to 60. D, Pocahontas, has way more letters. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we start with 10 factorial in our numerator, and then let's look at how many identical items we have. So we have 2a's, so divided by 2 factorial for 2a's. We've got O and O, so that's another 2 factorial. And that's equal to 1,814,400.